Hey, what's up YouTube? It's BeetlePlayer1011 here, and today we'll be talking about theorems of limits. So, in my last video I covered the basic definitions of a limit and explaining what a limit actually is. So, today we're going to be talking about the theorems behind limits and what you can do with them, mathematically speaking. So I wrote out the 5 major limits, theorems on limits here. But first let's talk about the condition for them to be true. It says that if the limit of f of x and the limit of g of x are finite, so, excuse my sloppy handwriting, but what this means is that so long as you have a graph here, I'm going to draw it out here, where you don't have some sort of extreme, meaning that if you have a graph that looks like, whoops, I'm still in the line. Basically, if you have a graph that does this, that limit is infinite, right? It goes infinitely upward at this point here. However, on every other point, if I take the limit here, for example, this limit exists. It's a finite number. It's a number that we can quantify. And if you remember, infinity is not a quantifiable number, rather it's just a concept. Now, considering this is the case, for all of these examples, I will be using x squared as the example, and just the limit of it as it approaches 2. And as you know, the limit of x squared as it approaches 2 is just 4, because 2 squared is 4. Now, let's talk about the first theorem. I'm going to bring it over here. So let's do this one in red. It says that the limit of k times f of x is equal to k times the limit of f of x. So what that means is that, let's say I have a function x squared being multiplied by a constant 4. I could just take the limit of x squared and then multiply by 4 later. So let's try it. So let's say I have the limit now as x approaches 2 of 4x squared. That equals, so we plug 2 in, we have 2 squared, which is 4. 4 times 4 is 16, so 16. Now the question is this equal to, so I'm going to put an equal sign and a question mark, 4 multiplied by the limit of x squared. And as you'll see, the answer is very clearly yes. So here, let's put x as it approaches 2. When we put this in, 2 squared is 4, and then we multiply 4 times 4 and we get 16. So we can check that off. And that's the first theorem. Now in the second theorem, let's do this over here. It says that the limit of the sum of functions is equal to the sum of the limits of the individual functions. So let's take this example. We have fx and g of x, so let's do x squared and x cubed at 2. So x squared at 2 is 4, plus x cubed at 2 is 8. So 4 plus 8 is, well, I lost my train of thought there. 4 plus 8 is 12, so we're going to put 12 here. And as you'll see, that what I'm writing here is literally the same thing you would do here, the same process. So we plug in 2 into f of x, and we plug in 3 later. And it's the same process, and what you'll still get is that 8 plus 4 is equal to 12. So we can check that one off here. Now let's go on to the third theorem. On the third theorem, we have that multiplying them will give you the same one as multiplying the limits. So let's take, for example, x squared and x cubed again, and what you'll get is that you'll have that the limit of x to the 5th should be equal to, that was a messed up question mark, but it should be equal to the limit of x squared times the limit of x cubed. And of course, all of this is being evaluated at 2. So, just looking at it, you can tell that this is true, but let's plug in the numbers. 2 to the 5th power is 32. And now is this equal to 2 squared, which is 4, times 2 cubed, which is 8. And what you'll notice is that 4 times 8 is indeed 32. So this theorem is also correct. Now, the next one is the division one. So here, let's again do x squared and x cubed. Now, this one has a bit of a caveat, and it's that the limit of g of x cannot be 0. So just thinking about it logically, anything divided by 0 is an undefined number, and we don't deal with that in very well in mathematics. So g of x cannot be 0 for this theorem to be true. But let's evaluate it. So what this basically says now, if we take f of x to be x squared and g of x to be x cubed, this will be the limit of 1 over x. Now, is this equal to the limit of x squared over x cubed? And what you'll get is that this is also true. So as x approaches 2, 1 over x becomes 1/2. Now, for this one, it's a little bit more complicated. 2 squared is 4, 2 cubed is 8. 4 over 8 is 1/2. So what you get is that they both equal 1/2. And that means that this theorem is also true. Now, the last one I think is best represented by a graph. So first, let's draw our graph. Now, the graph is just that x equals k. What that means is that the graph literally looks like this. So for every number x, the limit at that point is just going to be k. So at this point here, the limit approaching this point is still k. The limit approaching this point is still this letter k. Because there's no variable involved, the limit at any point will just be k. Now, let's go on to the second theorem, the Squeeze Theorem. And this one's a little bit more complicated, but let's give an analogy before I get into the actual mathematics. Now, let's say that I make a certain amount of money, right? So I'm Jay, I make a question mark amount of money. I know two things, though. There's a girl, Carolyn, and she always makes less than me. So I know that I always make more than Carolyn. And there's a second girl, Phoebe, and she always makes more than me. I should actually be more specific, or equal to. So here are two facts that we know. Phoebe always makes more than me, I always make more than Carolyn. So let's simplify this a bit. I am, in a sense, squeezed in between these two different people in terms of the amount of money we make. Phoebe always makes more than me, Carolyn always makes less than me, or equal to. Now, on a certain day, both Phoebe and Carolyn make $100. So, and she makes $100. This means that, logically, the only way for this statement to remain true is for me to have made $100 as well. Because I cannot make less than her, but I can't make more than Phoebe. You can think about it this way. For the statement, for this just I make more than Carolyn to be true, I can make anywhere equal or above 100. But I can't make more than 100 because Phoebe always has to make more than me. So this means that I have to make 100. And here's how it works in math. And you can look at this graph. G of x is always going to be greater than f of x. So g of x is always going to be greater than f of x. But f of x is always going to be greater than, I probably should have changed colors, but is always going to be greater than h of x. Now, this means the Squeeze theorem says that when you approach a certain point here, as you can see here, where the limit h of x is equal to g of x, then logically f of x must also be the same limit. Now, a famous example of this will be the proof for sine of x over x. I'm going to cover this in my next video tomorrow, but simply put, here's what we'll be proving. That the limit as x approaches 0 of sine of x over x is equal to 1. Now, there are multiple ways of proving this, and there's actually a really simple way once we get to derivatives, but we can also use the Squeeze Theorem. And the way we use the Squeeze Theorem is by coming up with two functions, one that is always greater than sine of x, and one that is always less than sine of x, and then we just have to prove that those two functions at this point both equal 1. So, thank you for watching this video, this next installment of limits. I hope to see you tomorrow where we will be continuing our discussion on limits. Thank you.